Welcome! In this session I'm going to explain the basic functional differences between the two-stroke engine and the four-stroke engine. And I'll do so by showing each engine functioning side by side. So in essence we'll see how similar functionally some stages are and how different others are, which will give rise obviously to the differences between the two engines overall. Of course these drawings of mine are for illustration purposes only, and of course they won't match the actual reality of a real engine. I've only drawn them like this obviously to explain my point. So just to begin with, let's just go over some key points on my diagrams. So my two-stroke engine is here, and this is my four-stroke engine, and these are the pistons of course of the two engines. And I'm illustrating small petrol engines, so we've got spark plugs here on both engines. And if we look further down, we've got the conrod here, or the connecting rod to be more specific, and here we've got the crankshaft. So I've illustrated the cylinders here, and of course for a four-stroke we call it the cylinder, but over on the two-stroke we tend to call it a pot. But in either case, whatever we call them, whether a pot or a cylinder, both these engines have pistons that reciprocate up and down within a cylindrical area, and that's why we refer to these engines sometimes as piston engines or reciprocating engines. They're the same thing in this case. So these are the flywheels of the two engines, and let's assume these two engines are a similar size and they've got similar size flywheels. I wanted to emphasize the little green stripes there because they represent the little vanes on the flywheels on these little engines that bring about an air cooling effect, and I'll show that later of course. And on a basic sort of engine like this, we've generally got above the flywheel there, bolted on, a magneto. And as most of us know, that's otherwise known as a coil pack. So leading out of each coil pack here are these electrical leads, or HT leads as they're otherwise known, and they terminate here at the spark plugs of course. Just looking back at the flywheel for a moment, these little two orange pieces here. These are what I've illustrated as little magnets. These are attached to the flywheel and rotate with the flywheel, and we'll have a look at what they do in a moment. Now both engines have an area here under the crankshaft with enough space to allow the crankshaft to rotate. But there are some big differences between these two areas in these two different engines. So we'll start with the four-stroke. As well as giving that space for the turning of the crankshaft, we've got the oil reservoir underneath here for the four-stroke of course, because we have to put oil in a four-stroke engine. And of course when the engine's not running, the oil just sits here, but when the engine's running it's sucked up this pipe through this filter here and up right through under the piston and up to the top here into the rocker area where it lubricates the rocker arms, the valves and the camshafts, etc. But what you'll notice in comparison on the two-stroke is it's a lot less complicated here at the top. We haven't got all those components we've just looked at there that the oil lubricates. And the two-stroke is also a lot less complicated down here as well. Unlike the four-stroke that has all this oil in the reservoir here, or the sump as we know it, the two-stroke actually has nothing down here. But as well as it being just a space to allow the turning of that crankshaft, it does have a really important role, and that is it works as a compression chamber. And I'll be showing exactly why that is very shortly. Some other key features here on the two-stroke are these areas here. This is what we call an inlet port, and this is an exhaust port. And if we have a look here on the four-stroke, we don't actually have these holes here in the cylinder. So rather than having an inlet and an exhaust port here on the four-stroke, instead we have an inlet and an exhaust valve. And so in comparison, the two-stroke engine uses these two ports, the inlet port and the exhaust port, to bring in fresh air and fuel for combustion and send out exhaust fumes, and the four-stroke engine does the same job by using these valves, an inlet valve to bring in fresh air and fuel, an exhaust valve to expel the exhaust gases. And that drawing in of the air and fuel of course and the expelling of the exhaust gases is done so via these areas here. These are the inlet manifold and the exhaust manifold. So now we've covered all of that, let's take a look at these two engines in action side by side. But before we start, let's just imagine now that this engine will be turning this way. And the main reason I've emphasised this is because this flywheel here will be turning in the opposite direction. So just to make it clear, both these engines run in the same direction. It's just the way I've orientated these two engines because I wanted to keep the two flywheels directly opposite each other there so I can explain my point better. So in the positions that they're in, this engine will be turning this way because we're looking at the back of one engine and at the front of the other. So let's imagine now then that the position that they're in, that we've got that little magnet part of the flywheel directly above on both engines here, and the pistons are in the uppermost point, so they're at top dead center. And from there on now we can imagine we've turned the key or pulled the pull cord and the engines are cranking. And for simplicity, of course, let's say that each engine is of the same size and is travelling at the same speed. So both pistons start to lower, and immediately there we can see on the 4-stroke that the piston has drawn in air and fuel above it. So it's both the drawing down of this piston, creating a suction and drawing the air and fuel in, and the opening of this valve allowing the flow of that air and fuel to actually come down the inlet manifold there into the cylinder above the piston. And so the opening of the inlet valve is timed perfectly with the induction here, with the induction of the air and fuel. And this is indeed referred to as the induction stroke. And the stroke meaning the downward stroke of the piston, so the induction stroke. So we know the importance of the inlet valve opening on the induction stroke. Now the way that it opens is by the turning of this cam. And although I haven't illustrated it here, the cam is part of a camshaft which is timed up perfectly with the turning of the crankshaft of the engine. So when the crankshaft is at a certain position, moving the piston downward, it would then turn the camshaft, allowing the inlet valve to open. And in order for me to explain that a little better, I'll zoom in just on this area here. So there we are, we can see a little better now, and we can see there that the exhaust valve is closed and the inlet valve is open. And we can now better see these components here. These are called rocker arms. And one thing we'll notice is that this rocker arm is tilted, and that's because of the camshaft I mentioned earlier. If we can see now, we can see that compared to the exhaust camshaft here, where the uppermost peak, the largest peak, is facing outwards out to the side, the one here on the inlet has rotated and is now facing upwards. And what that's done is it's forced the push rod here upwards as well, and in forcing the push rod upwards, it's tilted the rocker arm downward at the front because it's on a pivot in the middle there. And so in doing this, the front of the rocker arm forces downwards onto the top of the inlet valve, pushing the inlet valve down, overcoming the inlet valve spring there, which normally keeps the inlet valve up in the closed position, as we can see there with the exhaust valve. So now we can see how the position of these cams can affect the position of the valves. So the piston continues to lower, and that continues to draw in that air and fuel on the induction stroke. And whilst all this is going on in the 4-stroke, there's a lot less activity here in the 2-stroke. If we look above here in comparison, we can see that there's no air and fuel coming in yet. And structurally, of course, it's very different. If we look at the top of the cylinder here, it's just a closed off cylinder here at the top. Other than the hole for the spark plug, which the spark plug's filling at the moment, there's none of this valving system that the 4-stroke has. So it's a lot more simpler in this area in design. And as I've said, at the moment, nothing's really happening other than the fact that the piston's actually lowering. So we're not bringing in any air and fuel yet. Okay, so the pistons have come right down now to the lowermost point, and that's because the crankshafts here at the bottom have gone a full 180 degrees from top dead centre. And so at this point we can clearly see that the 4-stroke engine has continued to bring in that air and fuel on that induction stroke, but now we're at the bottom of the induction stroke now, we're at the lowermost point, so we can't draw any more in. But taking a look over here on the 2-stroke, things look quite different. All that's been achieved here so far is the opening of the exhaust port there on the left and the transfer port there on the right. So at the moment there isn't anything functioning. But going on further, the crankshafts are continuing to rotate, and that means the pistons are now rising. And if we take a little snapshot now of the position the components are in, the crankshaft has moved from its lowest position and rotated 90 degrees further. And this of course has allowed the pistons to travel halfway up their travelling distance within the cylinder. And now things are starting to look a little different. With the 4-stroke engine, we can see there that the inlet valve is now tightly closed and nothing can go back past it, and it's the same with the exhaust valve. So what's happening now is all of that air and fuel mixture above the piston is now being compressed because it can't go anywhere, and that's all down to the quick rotation of the cam there, allowing the highest point to turn facing out towards the side of the engine and allowing a lower point of the cam to sit the push rod lower, and that in turn allows the rocker arm to level out and the inlet valve then to go up back onto its seat because it's pulled back up that way from the pressure of the valve spring. So then with the 4-stroke engine we've got air and fuel up here being compressed, but if we take a look over at the 2-stroke engine we've still got nothing here above the piston, so there's nothing being compressed as yet. But what we can start to see here is air and fuel coming in from the inlet port and filling the crankcase area underneath the piston. Because what's happening there is the air and fuel is being drawn out of that inlet port by the rising of the piston. As the piston goes up, it's creating a vacuum behind it and drawing in that air and fuel. And as we can see, that's quite different to the four-stroke, because the four-stroke doesn't have any air and fuel underneath the piston at all. All there is underneath the piston is the oil in the sump and some components. So we've got air and fuel at the top of the piston only with the four-stroke. Okay, so let's continue. And now both crankshafts have rotated another 90 degrees. And that now means that both pistons are now at their uppermost point. So we call that top dead center. And let's notice there that although the pistons on both engines are at top dead center, each engine is of course doing a different thing. The piston on the four-stroke here has just finished its compression stroke. So when the piston was travelling down before, it was the induction stroke, bringing in the air and fuel, and now it's gone back up, it's compressed that air and fuel, and it's the compression stroke. So we've finished the compression stroke there, and we've compressed all that air and fuel, ready for the combustion process. Now what I want to explain before I go any further is that this is only a very basic model of how these engines work, and I fully understand that the combustion process probably won't take place exactly like this. Combustion probably starts a little earlier than this, than top dead center, and so on, and the same with all the processes. I'm only showing a very basic model for beginners. I don't want to give too much information and make things too complicated to begin with. So let's just take it for now that we're at top dead center on the compression stroke. Okay, so we'll move over to the two-stroke, and of course the piston's in exactly the same position, but there's nothing up there above. We haven't compressed anything yet. But as the piston rose to top dead center, it created more of a vacuum beneath it and drew in more of that air and fuel mixture from the inlet port there. And so at this point, that air and fuel is all over the crankcase. So the crankcase is absolutely saturated with that air and fuel mixture. But at this point, when these pistons are at top dead center or near top dead center, these magnets here on the flywheel that we looked at earlier are specifically placed on the flywheel so that when each piston is at or near top dead center, they line up with each coil pack. And of course the magnets don't just line up and stay there. They're on the flywheel, so the flywheel's moving very fast. They actually pass this point. So each magnet travels past the coil packs at high speed. And right at the point in which they pass, electrical energy is generated and transferred from the magnet into the coil pack. So just at that split second on that passing point, all of that generated energy is fed into the coil pack, and then it goes further on into the HT lead. And again, in a split second, that travels all the way up the HT leads to the spark plug, where it activates the spark plug to create a spark inside the cylinder. So there we have it then. We've got a spark generated on both engines, on the four-stroke here and on the two-stroke, and even though there's no air and fuel mixture there to combust for the two-stroke, there's still a spark, because it's timed just so that each time the flywheel magnet passes the coil pack, the piston's always at or near top dead center, which is true for the four-stroke as well. So to sum it up, because of this, there'll be a spark when the piston's in this position, whether there's fuel up there to combust or not. And of course, because a spark has been generated here in the two-stroke, it will remain small because there's nothing there, no air and fuel to ignite. But let's compare that now to our four-stroke. Of course, we've got a large spark there generated because we've got that air and fuel in there. So it's starting to ignite that air and fuel. So that spark ignition's now spread, and it's caused a mini controlled explosion inside the cylinder. And that explosion forces the piston back down. So an important thing to mention now is that until this point, where the four-stroke engine is now generating power and forcing the piston down itself and creating its own movement, the movement of both engines were down to the starting process from either the starter motors or the starter pull cords, etc. And of course, because the two-stroke hasn't yet created any combustion for its own movement, it's still moving from the operator's starting process. But for simplicity, let's still imagine that they're moving at the same speed, but they most probably wouldn't be in reality. Just quickly going back to this diagram, from this point here, when there's been a huge explosion which has forced the piston back down, we call this the power stroke. And what's left behind here in the wake of all this combustion are the waste products here. We call these the exhaust fumes, of course. So when the piston's on its way back down, we find here that the exhaust valve opens just slightly. And although at this point that might seem a little premature because the piston isn't yet coming back up and forcing the fumes out, the reason it actually does that is to allow some air to come in from the exhaust side, which is vital because if there wasn't, the piston wouldn't be able to travel down properly because there would be a vacuum there. And at the same time, a nice flow of fresh air coming into those exhaust fumes help to dilute them so that when the piston rises again, all the exhaust gases can be flushed out that bit better. So let's have a look at what's going on at the same time with our two-stroke then. Of course, the piston's coming back down, and that stopped the air and fuel from being drawn in from the inlet port there, because what's happening now, as the piston's lowering, it's actually starting to compress that air and fuel down there in the crankcase, rather than there being a vacuum. If we take a look now at both flywheels, because the pistons are in this position, we see that the flywheel magnets are actually facing in different directions. We've got this one here, and the other one is on the opposite side in the same place. So as we saw, they were here at the top, but in this little snapshot of time, they've moved 90 degrees round with the crankshaft. Now both pistons are at their lowermost points because the crankshaft has turned a full 180 degrees from the piston's top dead centres. And we can see in the four-stroke here that it continued to bring in that nice flow of fresh air into the cylinder, all thanks to the exhaust valve being opened by the timing of the cam there and the rocker arm. And if we compare all this activity now with the activity going on here over in the two-stroke, then we can see that there are so many differences between the two engines. So as the two-stroke piston lowered, it created a pressure beneath it, and in doing so it compressed all of that air and fuel mixture. And because it was compressed, there was a pressure there that needed to be released in order for the piston to come down to its lowermost point. But the pressure couldn't go back through the inlet port here because the piston is blocking its route. So the only way for that pressure to go now, the piston's in this position, is this way through the transfer port, which is open now specifically because the piston is sitting in this position. And the pressure beneath it continues to push all of that air and fuel into the cylinder area there above the piston. Now, although I've shown that the air and fuel has gone from the crankcase now, but in reality there would probably be quite a lot of air and fuel still hanging around in this area. I've just illustrated it this way to show the flow of air and fuel. But as that mix of air and fuel passed through, it lubricated all the components, all the crankshaft, the bearings and the cylinder, because the fuel has with it the two-stroke mix oil. So wherever that fuel-air mixture goes, it's lubricating, and it's doing the same up here, so that when the piston rises, there's going to be lubrication between itself and the cylinder walls. And that's quite different to the four-stroke engine. The only means of lubrication in the four-stroke is by use of this oil down here in the oil reservoir in the sump area, because no lubricating oil whatsoever is coming in with the fuel on a four-stroke engine. It's just the fuel itself. So there are some big differences between the two there. Something else worth noting whilst the pistons are at the lowermost point is the magnets on the flywheel are both facing the bottom of the flywheel at the moment, which is where they should be, because when the crankshaft has turned another 180 degrees and the pistons are at their uppermost point at top dead centre, those magnets will be travelling past the coil pack. So that's a similarity for the both of them. So let's continue with the workings, but before we do, let's just take a look here on the two-stroke, on the exhaust port. We can see there that it's open, and you'd think that some of this mixture, this air and fuel mixture inside the cylinder here, would be lost out of there, and indeed some actually is, but there is a good reason why it stays open, and that will become apparent very shortly. But there are some design of two-stroke engines that operate a little valving system here to prevent any of this air and fuel escaping. Okay, so the pistons are ready to go back up now, and now the crankshaft has turned another 90 degrees, and that means that the pistons are halfway up their travel distance within the cylinder. And if we take a look above the pistons there, we'll see that there's something very different going on between the two. First of all, let's have a look at the two-stroke. As we can see above the piston there, we've got the air and fuel that came out of the transfer port is now compressing. And it's compressing now nicely up in the top of the cylinder there, because both the exhaust port there and the transfer port are now blocked off by the piston itself. So this is the first time since we've been rotating the crankshaft that the two-stroke is getting ready with its air and fuel ready to combust. But this is where the clever two-stroke piston is working as a piston and a pump, because as it's going up compressing that air and fuel, it's creating that vacuum again behind it, drawing in air from the inlet port there into the crankcase. So it's doing those two things at the same time. And of course what that means is it's getting the air and fuel into the crankcase here ready for the next cycle. And again it's lubricating all those components as it flushes through. And in comparison, that's very, very different to what's going on here in the four-stroke. Of course, the pistons are at the same level, they're going at the same speed. So at this point now, what's happening is the rise of the piston is pushing out all of those products of the last combustion. So all of those exhaust fumes going out through the exhaust valve there, because the exhaust valve's open a little bit more now to allow all of that to be flushed out via the exhaust and into the environment. And if we just quickly note that the inlet valve is shut now, so that there's no chance that any of these exhaust fumes can go back through the inlet and towards the carburettor. And because at this point the rising stroke of the piston is pushing those exhaust fumes out, we call this the exhaust stroke. And if we have a look below the piston here, we can see how different it is to the two-stroke. There's no compression down here, so there's no air and fuel coming down here to be compressed and transferred up to the top of the piston. And indeed, this piston is acting as a piston only, rather than a piston and a pump, like the two-stroke. So again, with each piston in this position, if we look at the magnets on the flywheels, there's the one on the two-stroke and the one on the four-strokes in the same position on the side we can't see. We'll see there that they are now positioned 90 degrees before the coil packs, so that when the pistons actually get to the top dead centre, they'll be passing the coil packs 90 degrees later, if you like. And there we go, we can see that now. So now both pistons are at top dead centre, and what's happening between the two pistons are very, very different. The four-stroke piston is forcing out the remaining exhaust fumes, and the two-stroke piston has compressed all that air and fuel together, ready for the explosion of combustion. And at the same time, as it travelled up, it drew in all of that air and fuel and got a good concentration of it down there, waiting for the next cycle. Again, that doesn't happen here in the four-stroke. Of course, now the pistons are in this position, those magnets on the flywheels are going to instantaneously past the coil packs, generating and transferring the electrical energy, which again of course travels up each of the HT leads to the spark plugs. That again stimulates each spark plug to fire, and there's still a spark here on the four-stroke, even though we're at the end of the exhaust stroke, and there doesn't really need to be because it's not a power stroke. It still sparks because that magnet that passes the coil pack does so every 360 degrees, and that generates the spark. So there's going to be a spark whether it's on an exhaust stroke or a power stroke, and that neither provides a benefit or a detriment to the engine. It just happens because of the timing of the electrical system. Some people believe that this extra spark helps to burn up any extra gases that haven't yet been burnt up, and if it does that, great. But in either case, I'm just illustrating here that the exhaust fumes have been pushed out of the exhaust manifold and the exhaust valve is now shut. I'm not saying every last bit of exhaust fumes will be gone from here, but I'm just expressing that this is the point at which they're pushed out. But over on the two-stroke here, we're on a power stroke, so that spark is now igniting that air and fuel. And of course that ignition spreads rapidly into a mini controlled explosion. And as we know, this forces the piston downwards with great pressure, and left in the wake there from the explosion is all those exhaust gases again. And at this point we'll just take a little snapshot of what's going on with both engines. We'll see the differences here. And at this point then, we've got both pistons that are halfway down their travel point down the cylinder, and that's because each crankshaft has turned another 90 degrees of course. And the four-stroke here is on inlet again, so it's drawing in that air and fuel out of the inlet manifold because the piston's travelling down and it's drawing in all that air and fuel with a suction action. And of course the inlet valve's open at the moment because the timing's correct, and so both pistons continue to travel down. And if we have a look here on the two-stroke at this point, we can see that the air and fuel underneath the piston itself is starting to compress. The piston itself's compressing that air and fuel again, which has come out of the inlet port there when the piston rose on its last upward stroke, making it all ready to transfer to the top of the piston as it lowers. And let's of course remember that because the pistons are now halfway down their travel distance in the cylinder, because the crankshaft's moved 90 degrees, so has the position of each magnet. So we've got one here and one here. So from there, let's imagine that the pistons again have come right down to the bottom, so at the lowermost point. And that means of course the crankshafts have turned another 90 degrees, so they've turned a full 180 degrees from top dead centre. And let's compare the two with what's going on here. The 4-stroke engine continued to draw in all that air and fuel there as the piston lowered, and now it's filled the cylinder. Now in comparison, as we saw before, the 2-stroke's also drawing in that air and fuel, but in a very different way. Just to quickly cover it again, the air and fuel's coming out of this transfer port here, because as the piston's lowered, it's compressed all of that air and fuel below it there and forced it up here through the transfer port and out to the top, as we saw earlier. And as it does so, it flushes in and pushes out all of them exhaust fumes into the exhaust port. So in comparison then, we can see that the air and fuel is being drawn in on both engines quite differently. On the 2-stroke, it's being drawn in from the transfer port here to the top of the piston, and here on the 4-stroke it's being drawn in from the inlet manifold there. So just reverting back to the 2-stroke for a moment, we can see that with every downward motion of the piston, fresh air and fuel is brought into the cylinder and exhaust gases are forced out. And so if we look at both engines at this point, both cylinders are charged and full of air and fuel. But now both pistons are ready to rise again, and of course they do so. And so we find ourselves in a position now where both pistons are on their power strokes, so they are compressing that air and fuel ready for combustion. So looking over here at the 2-stroke, we've got some good compression going on there because the piston has blocked off the exhaust port and the transfer port, and behind the piston now is drawing in, so creating the vacuum again and drawing in air and fuel in there from the inlet port. So we've got the compression there, and the 4-stroke engine's achieved its compression because the inlet valve's closed there, and so is the exhaust valve, because we've got the timing on the 2 cams there that are just so to allow that to be. And again, both engines are at the same state now. They're both on the compression stroke. And if we continue now and let the crank turn, the pistons rise because the crank's now turned another 90 degrees, and now we're at top dead centre. Of course, it's top dead centre on compression stroke, so we've compressed all that air and fuel, and now we're ready for a spark. And that spark will now be generated because we've got the magnets there that are passing the coil packs just at that point at the top on the flywheel. So it's producing the current and it's going up the HT leads and down to the spark plugs. This of course happens more or less in an instant, but there it is, the spark. And the result is that instant explosion, that combustion there. That again generates enough power to force those pistons back down and leave behind in its wake all those exhaust gases. And as before, with the 4-stroke, the exhaust valve opens slightly as the piston lowers to bring some of that fresh air in to whirl round with the exhaust fumes, which helps to dilute them and helps clean the cylinder, and also helps the piston to lower that much better without it being caught in a vacuum. And on the 2-stroke, as we know, there are no valves to open, and there may well be a small vacuum for a very small distance of its travel. But as soon as we go a bit lower and open those ports there, any vacuum that may build up in there will no longer be a problem. And so again, we've got two very different things happening in these cylinders between the two of these engines. On the 4-stroke, we've continued to bring in that air as the piston lowered, and it's mixed around with the exhaust gases. And in the 2-stroke, the fresh air and fuel has come in through the transfer port and is now forcing the exhaust fumes out through the exhaust port. And at the same time, the pistons blocked off the inlet port so no air and fuel can come in, but it wouldn't be able to anyway because there wouldn't be a vacuum because the piston is at its lowermost point. And both pistons are coming up again now, and we can see on the 4-stroke that the exhaust fumes are being forced out there through the exhaust manifold by the piston. But in comparison with the 2-stroke over here, we've got a compression stroke going on here again, so we've got all that air and fuel above the piston, which will soon result in combustion. So as this piston rises, it forces out all of them exhaust fumes, and as this piston rises, it's creating another compression stroke leading to a power stroke. Going on from here and allowing the pistons to rise again, we know what's going on now. On the 2-stroke here, we've got the full compression because we're at top dead centre, and it's the same over here in the 4-stroke, and it's pushed all of that exhaust gases out now through the manifold, and there's only a small amount left there. And at that point, we know that our magnets align up or just past the coil packs there, so that's creating the electricity up through the HT leads to a spark once again. And we know that the spark here on the 2-stroke is going to result in combustion again, and also we've got the spark here in the 4-stroke, even though it doesn't need a spark as we've already been through. It's on the exhaust stroke. It sparks because of the magnet passing the coil, so it'll spark on every revolution of that crankshaft, so every time the piston's at top dead centre, whether it's a power stroke or an exhaust stroke, and it's neither a detriment to the engine or an advantage. So I hope that's explained some of the basic functionalities, and it really is the basic functionalities. And in reality, both these engines wouldn't run at the same speed like this probably. There'd be different weights, but we're just going on an example here so that we can get the differences in functionality. But what I want to do is let the animation run now so that we can see things now a little clearer for a few moments. I'm hoping I've explained there a lot of differences on a functional level, but now what I want to do is explain the differences between how these two engines lubricate themselves. I know I've gone through on the two-stroke on how the oil comes in with the fuel, but if I just explain on the four-stroke a little clearer. Of course, as I mentioned before, the four-stroke here has its own reservoir in the sump area, which of course is filled to the appropriate level with the appropriate oil. So of course the difference is we keep the oil separate from the fuel on the four-stroke, and the weight's distributed around the engine is via this pickup pipe here, and it's the oil pump here that creates that flow. So in the pickup pipe here on this side of the oil pump, there's obviously a vacuum there sucking the oil in towards the pump itself, and then the oil goes through the pump and is forced out this way upwards, and there's a positive pressure here pushing the oil away from the pump. So the moral of the story is that all the flow and movement in this pipe is created by the pump. Now before the oil's distributed round the engine, it goes through this little filter here, and that just filters out all the main impurities to make the oil a little safer to use. And so then it's distributed right up along this pipe, and as it does so, it's lubricating all those vital areas there. And as we'll see shortly, there's a little nozzle there that sprays oil upwards into the cylinder to allow lubrication between the piston and the cylinder. And then the lubrication goes further up here to the rocker arms, because the rocker arms are always moving, and the valve stems. And at the same time it provides lubrication for the two cams here, which are always turning to allow movement for each valve. And this pipe obviously supplies oil to the crankshaft as well, and generally what we find is that there's a micro hole down the centre of the crankshaft there, but the pipe normally brings up the oil to that area, and the oil is then fed down the centre there of the crankshaft to the big end bearings, and that oil is also distributed to the main bearings here. So I've been saying that the oil pump creates all this flow, so it's creating all this energy. So where does it get its energy from? And it does so from the crankshaft. It's geared directly from itself to the crankshaft. So every time the crankshaft turns, it turns the gear of the pump, and that creates the turning motion inside the pump for all that movement. So the oil's now reached the extremities of the engine, if you like. So you could say now that the engine's in a lubricated state. And you can see now how much they differ in design when it comes to the lubricating system on these engines. The two-stroke is so much simpler in the way that it draws in the oil with the fuel and lubricates all those components as it passes. There does exist a simpler method of lubrication in four-strokes, and that is the inclusion of a protruded area made of metal on the bottom of the big end bearing, and as the crankshaft turns, that dips into the oil reservoir there and flicks the oil up and splashes it. It's a splashing mechanism of lubrication, and this type of lubricating tends to be on the smaller engines with the single cylinders. Okay, so now we've looked at the basic principles of how these engines are lubricated, we can now look at the basic principles of how these engines are cooled. And cooling is extremely important, of course, because we've got thousands of mini explosions per minute going on inside the cylinder, as well as all that friction of all those components moving against each other. So there's going to get a lot of heat in there. And if we're going to prevent engine seizure, then we've got to keep these engines nice and cool. And that first brings me to the flywheels. Earlier on, I emphasised these green areas, what are called the vanes on the flywheels. They're more specifically referred to as air vanes, and as the flywheel turns, so as the engine's running and the flywheel's turning, them air vanes are protruding out from the flywheel and they're generating an airflow. And on these type of engines, known as air-cooled engines, all the air is flowing around the engine and just taking away the heat. So it's generating an airflow with the environment past the engine and out to the environment again. So it's bringing air, cool air in from the environment, spreading it round the engine, and then that air is then forced out into the environment warmer than it was when it went in, taking with it some of that heat from the engine and leaving behind a slightly cooler engine. Now both 4-stroke and 2-stroke engines can have this type of cooling system, but it's mainly seen on the small 2-stroke engines like on chainsaws, etc. But they are also on small 4-stroke engines. But what we normally tend to see on a larger 4-stroke engine is a water-cooled system. And I'll just go through that very quickly. And that's where these areas come in as important on the 4-stroke, because they are hollow cutouts between the cylinder and the outside environment where the water is pumped through. So cool water's pumped through these areas and it cools the engine down as it's pumped through. And this system, of course, has its own water pump and radiator and fan to keep all this water cool and allow it to circulate through the engine. And as that cool water circulates through the engine, it takes away from the engine a lot of that heat, allowing the engine to keep cool. And when I say circulating through the engine, I don't mean through the actual engine itself into the cylinder. As you can see there, it's in a special compartmentalized area there, so it can't get into the engine itself. And that comes to the end of this session on the very basic principles of a 2-stroke and 4-stroke comparison of function. And that's the important part I want to emphasise. It's just the functionality of these two engines I've compared on a basic level, because a comparison of the pros and cons of each and where we would fit each, so what application we would use them for, is a whole video in itself. So I want to thank you so much for watching, and I'll be back soon.